Welcome to class. In this video, we're going to discuss complex numbers. So let's talk, first of all, about something called an imaginary number. An imaginary number is represented by the letter I, and it is equal to the square root of -1. Now, normally we would say that you can't take the square root of a negative number, but keep in mind that what we really mean when we say that is we won't get a real answer when we take the square root of a negative number. So the square root of -1 is called I. Then, if you were to square that, you would have I squared equals the square root of -1 squared. And you'll notice the square root and the square would cancel to leave us with -1. So it's really important to know that I is the square root of -1, but you also need to know that I squared is equal to plain old -1. So for example, let's say we need to simplify the square root of -25. We can break this up into two separate square roots because -25 is the same thing as 25 times -1. That means I'm taking the square root of 25 and the square root of -1. Now the square root of 25 is 5 and the square root of -1 is I. So the square root of -25 is 5i. Notice that the I comes after the number. So if I want to do, for example, the square root of -64, I'd write this as the square root of 64 times -1, or square root of 64 times the square root of -1, and this is going to be 8i. Again, notice that I have the number before the letter I. Now, an imaginary number is a number that has a constant directly preceding an I. However, we also have what are called complex numbers. These are numbers that mix real and imaginary parts. So the real part has no I. The imaginary part is added or subtracted to the real part, and it includes an I. This is called standard form of a complex number when you write it as the real part plus the imaginary part. If something asks you to write the complex number, it should be written in this standard form unless you are told otherwise. Now, one of the other things I want to point out about the information you see in this box is if b equals 0, then a plus bi is a real number. And if a equals 0 and b is not equal to 0, then the complex number is imaginary. In other words, it is possible to have a complex number that gives you something that's just real if the bi is not there. Or if you have no a in front of the bi, then that's still technically a complex number, but it's only the imaginary part. So we want to simplify square roots that have negatives in them the same way we would simplify other roots to the best of our ability. Now we already did one problem like this where we took the square root of -25, but -24 under the square root requires us to simplify a little further. So here, let's go ahead and start by just breaking this up a little bit. I could very simply call this 24 times -1 underneath the square root. And that's really the square root of 24 times the square root of -1, which is the square root of 24 times I, where I is outside of the square root. However, this is not simplest form because square root of 24 is further simplifiable. So a lot of times what you'll see is rather than doing this and then simplifying the square root of 24, a lot of times what people will do is when they start with this first step here, they'll go ahead and break 24 up while they're breaking everything else up. So here, 24, I happen to know, breaks up into 4 times 6, and then again, I really have -24, so I have my -1. So this is the square root of 4 times the square root of 6 times the square root of -1. The square root of 4 is 2. I don't know the square root of 6, and it doesn't break down anymore. And square root of -1 is I. So you see, by doing it all in one step, you're actually going to save yourself a lot of work. But if you don't see that right away, you can always continue to simplify later as you like. Now let's talk about powers of I. This is sometimes also known as the cycle of I. Because if you have I to the 1, you're going to get I. But if you have I squared, we've already discussed this, you're going to have -1. So what do you get when you do I cubed? Well, I'm going to break I cubed up into I squared times I. I know I squared is -1 and I is I. So this is really -1 times I, or negative I. Okay, then we could do I to the 4th, which you would write as I cubed times I. We just said I cubed is -1. So when I multiply that by I, I'm going to get -I squared, which is -1, which gives me 1. Okay, so you're going to notice that we can work through this and you can power through it. But what if you want I to the 15th or 38th or 1,462nd? Well, that's going to make it a little more difficult. So this is where we want to start talking about how this is a cycle. So I to the 1 is going to be I. But I squared is -1. I cubed is -I. I to the 4th is +1. And then it's going to cycle back up. What does that mean? Well, notice that I to the 1 is the same thing as I to the 5th. And it's also the same thing as I to the 9th. This is because if you are thinking about it almost like a clock, every time you get back up to the top of the clock, you're going to return to I. Notice that you could do the same thing with I squared, matches I to the 6th, and then it would also match I to the 10th. And it's a lot easier to recognize this pattern than it is to calculate out your powers of I every time. So how does this work? Let me just give you a quick summary here. You're going to take the exponent of your I and divide it by 4. Whatever your remainder is gives you the exponent that it aligns with. So for example, if I have I to the 18th, well, 18 divided by 4, 4 goes into 18 4 times, 4 times 4 is 16. I have a remainder of 2. That means that I to the 18th is the same thing as I squared, which is -1. So as long as you know your first 4 in the cycle, you can use this remainder concept to help you find the value of your version very simply and very easily. Go ahead and use this method we just learned in order to try and evaluate I to the 35. And when you've done that, replay the video so that you can check your answer. Okay, so in this case, I'm going to divide 35 by 4. 4 goes into 35, almost 9 times, but not quite, so it's 8. 8 times 4 is 32. This gives me a remainder of 3. So I to the 35 equals I cubed, which, if you remember, is the equivalent to -I. When you're doing this type of problem, your final answer should have no more than 1 in the exponent. You can have a real number, or you can have something times I. Okay, so really, again, remember your choices should be I, -1, -I, or +1. Because once you get to +1, you're going to cycle back through these 4 options. So how do we graph things like this? Well, of course, this is going to be just a little bit different than what we're used to, and that's because we're talking about a real component and an imaginary one, rather than an x and a y component. So what we're going to do is we're going to label the x-axis as the real axis and the y-axis as the imaginary axis. So for example, if I wanted to plot the point 3 plus 2i, so I want to plot that number, I'm going to count 1, 2, 3 to the right, and 1, 2 up. Notice you'll normally have tick marks like a normal graph. And that is going to be the point 3 plus 2i, because we've done 3 real. So I want you to go ahead and try to plot the complex number 3 minus 4i on the complex plane. Remember, your steps are going to be determine the real part and the imaginary part. And you're going to count by the real part. Right is positive real, left is negative real. Then you'll count vertically, either up if your imaginary number is positive, or down if your imaginary number is negative, and you'll plot the point. Take a moment, and then you can play the video again when you've tried that. So hopefully, with 3 minus 4i, you counted right 3 and down 4, and plotted this point right here, which, if possible, if you have any sort of paper that allows for it, I would go ahead and label with the value as well. Now, let's say that you want to add or subtract complex numbers. The key to this is going to be grouping the real parts and the imaginary parts. Notice that when you're adding complex numbers, so this first one, you have A plus C is the real part. Similarly, you have BI plus DI, or you can factor out the I, B plus D times I. This holds true when you're doing subtraction as well. You have A minus C for the real part. And for your imaginary part, you're going to have BI minus DI, which comes out to be B minus D times I. So hopefully this is, kind of an intuitive option for you. And let's go ahead and take a look at what this looks like in a practice problem. So I would recommend that you go ahead and try the first of these. Just add the two complex numbers together and then press play when you're done. So here I have 3 minus 4i plus 2 plus 5i. Notice here that my real parts are 3 and 2, so 3 plus 2 is going to give me 5 for the real part. Then my imaginary parts are negative 4i plus 5i. And negative 4 plus 5 is 1, so that's a positive 1i. However, because it says 1i, I'm going to go ahead and ignore the 1. You generally don't put a 1 in front of an I, just like you wouldn't say 1x. So our complex numbers standard form is 5 plus I. Now when you are doing the subtraction for the second problem, 2 plus 5i minus 3 minus 4i, it is important to set it up as you see here, where each of the complex numbers is in its own set of parentheses. So go ahead, start by distributing your negative, and then combining like terms, and then come back and press play on the video again. So if I were to distribute my negative, it becomes 2 plus 5i minus 3 plus 4i, and then I can say, all right, I have 2 minus 3 is going to give me negative 1, and I also have 5i plus 4i, which gives me plus 9i. Now, notice that you don't have to do the distribute method if you don't want. You can do it the way that we were talking about before. If you did that, notice here that it would be 2 minus 3 still gives you negative 1, and 5i minus negative 4i is also going to give you 9i. I, however, do like to distribute, partially because it's how I would do it if it were with x's instead of i's, and partially because I like to make sure that I don't miss a sign change when it shows up. So now let's say that you have a complex number and a real number and you want to multiply them. The great news is that this is very simple. You just need to use the distributive property and, if possible, simplify by combining like terms. Go ahead and try it on this problem and then press play when you're ready. So here, if I were to multiply through by 4, I'm going to do 4 times 2 is 8, and 4 times 5i is 20i. So this comes out to be 8 plus 20i. Simple enough. But what happens if I have two complex numbers instead of a complex and a real number? Well, what we're going to do here is we're going to use the FOIL method. So you're going to FOIL it out. And remember, if you come up with anything that has I squared in it, you'll need to replace it with -1 and combine like terms. So when they say simplify in this case, they are saying replace anything with I squared in it with -1 and simplify. So go ahead and give that a try really quickly. Okay, let's go ahead and FOIL. So first, 4 times 2 is 8. Outside, 4 times -5i is -20i. Inside, 3i times 2 is 6i. And last is 3i times -5i, which is -15i squared. So at this point, I'm going to add down. I have 8 minus 14i, and then minus 15i squared. Since I squared is -1, I could write -15 times I squared is -15 times -1, which is +15. Now 8 and 15 are both real components of my number, so I can add them together and get 23 minus 14i. Notice that the real part still comes before the imaginary part. Now, let's discuss the concept of a complex conjugate. A complex conjugate is one where you take a complex number and you switch the sign of the middle. So if you have a plus bi, its complex conjugate is a minus bi. Notice that nothing actually changes other than the sign in the middle. So for example, if I gave you 5 minus 6i, its complex conjugate would be 5 plus 6i. And the complex conjugate of 5 plus 6i is also 5 minus 6i. So they are complex conjugates of one another. Why do we care? Well, when a complex number is multiplied by its own conjugate, the result is a real number. Also, when it is added to its own complex conjugate, the result is a real number. So for example, if I did a plus bi times a minus bi, and I FOILed that out, I'd get a squared, then minus abi, plus abi, and then it would be minus b squared I squared. Notice that these would cancel, and then have a squared, and minus b squared I squared is really just plus b squared, because we know I squared equals -1. Similarly, if you wanted to add a number to its complex conjugate, a plus bi plus a minus bi, the bi and the negative bi would cancel, and you'd be left with 2a. So complex conjugates let you work with complex numbers, and they'll end up being real numbers. So keeping in mind that our two options here are two practice problems, 2 plus I times the root 5 is really more often written as 2 plus root 5i, where the I is definitely outside the square root. And B, -1/2 I is the same thing as 0 minus 1/2 I. Go ahead and find the complex conjugates of each of these two numbers. So for A, the complex conjugate would be 2 minus root 5i. Notice that I did not say that 2 plus root 5i equals 2 minus root 5i. Okay, these two things are not equal to one another. So if you wrote that they were equals, erase that, and you want to relabel it as the complex conjugate. And the complex conjugate of 0 minus 1/2 I is going to be 0 plus 1/2 I, which we would normally write simply as 1/2 I. So at this point, I want you to go ahead and be able to apply this, because when we're doing complex division problems, we're actually going to do them by multiplying both the top and the bottom of the problem by the complex conjugate of the denominator. So notice our steps. First, we're going to write the division problem as a fraction. So 2 plus 5i divided by 4 minus I, we'll write as a fraction. Okay. And at this point, again, our next step, it says to determine the complex conjugate of the denominator. Well, my number is 4 minus I. Its complex conjugate, therefore, is 4 plus I. And we're going to multiply the numerator and denominator of the fraction by that. So in order to do that, I have to put parentheses around both the numerator and denominator. And I'm going to multiply both by 4 plus I. Go ahead and take a moment to multiply out both the numerator and the denominator. And then we'll talk about simplifying them. So now that you've had a chance to try this on your own, let's take a look at this. In the numerator, when I multiply it out, I will FOIL. 2 times 4 is 8. 2 times I is 2i. 5i times 4 is 20i. And 5i times I is 5i squared. In the denominator, I chose to use my rule, a plus b times a minus b equals a squared minus b squared. That's an old school rule from algebra. And when I do that, I get 16 minus I squared. Now that I've done the multiplication, I need to simplify. Simplification is the same as if I were just doing multiplication on its own. What that means is I'm going to start by combining my like terms. 2i plus 20i in the numerator is going to be 22i. However, this plus 5i squared is really going to be minus 5. In the denominator, I can carry down my 16, and minus I squared is really going to be plus 1. Now I combine my like terms. In the numerator, that's 8 and negative 5, give me 3. And I carry down my plus 22i. And in the bottom, I have 17. Now, some people will be tempted to stop there. However, simplifying is going to really require us to put it into standard complex form. So if you are a person who doesn't remember that, you might want to go ahead and add a 5th step and say write in standard form. Remember, standard form for a complex number is going to be a plus bi. This means that in this case I don't have that because I have a plus bi over some c. So in order to put this in standard form, I'm simply going to split the fraction. 3 over 17 plus 22 over 17i. Now it is in the a plus bi format. I hope that was helpful. I'll see you in the next video.